Good morning, everyone. Hope you're all well. Dr. Bennett here, and today we're going to start off chapter 7 by looking at centroids and centers of mass. Now, the concept of the center of mass should be fairly familiar to all of you. The textbook kicks off by discussing the center of mass of this woman who's doing this kind of like yoga pose type thing, right? So in order to support herself, her center of mass must be directly above where she's supporting herself with her hands, right? Otherwise she would fall over. So that's just a fairly simple example of how we're going to be dealing with centers of mass in this chapter. So up until now, we've basically considered only point forces or loads acting on a structure. So for example, with a truss, for example, like this bridge, we've considered point forces acting at the joints. We've considered point forces acting some way along one of the members, like in a frame, for example. But what if we want to consider something actually on the bridge itself? So let's say, for example, we have a lorry or a truck on the bridge. In order to work out where the force is applied, we need to work out where the center of mass of the truck is, and then consider that as a point force acting at some point on the bridge. And that's fairly easy to do for simple shapes like squares and rectangles, but for more complex shapes we need to work out where the center of mass of that shape is using some different techniques, which we'll get onto later in this tutorial. So for a two-dimensional shape, which is what we're going to deal with initially here, the center of its area is called a centroid, and this is going to tell us where the center of mass is for any given shape. And the way we calculate that is using a weighted average. So what we do is we take a more complex shape, we split it up into smaller pieces of shapes that we know how to deal with, like squares and rectangles. We find the center of mass of each of those smaller pieces, and then we average the relative position of those center of masses to find the center of mass of the total shape. So at this point, the eagle-eyed among you will have noticed that I can't spell centre consistently, and that's because the American spelling of centre is ER, and in British it's RE. So I'm doing my best to keep up with the American spelling, but I may flick back into British mode occasionally. So a good way to think of the weighted average is to think about how you would balance a system, like a scale or like a seesaw, for example, right? So if you consider this system here, we have multiple blocks, all of mass 1, positioned at different places along the x-axis. And what we would like to try and find is basically the point at which the left-hand side balances the right-hand side. So you can see intuitively that it's going to be somewhere around this area here, right? So there's 12 blocks in total. There's 6 stacked up here at position 8 along the x-axis, 3 at 5, 1 at 4 and 2 at 2. So in order to balance this system left and right, if I think about where my fulcrum point would be, I'm thinking it's going to be somewhere around here initially. So how do I calculate that? Well, I think about where the blocks are in relation to their position on the x-axis, how many are in that position, and then average that by dividing through by the total number of blocks. So the average x position of the weight, which is what we're going to try and find, we denote as x bar, is equal to the x position multiplied by the number of blocks in that position, right? So we take x1 multiplied by b1, add that to x2 multiplied by b2, and so on and so forth. And then we divide that through by the total number of blocks. So that can be written in summation form, where we say the sum over I of all of the xi's multiplied by bi divided through by the total number of bi's. So the sum over I of all of the bi's. So for our example above, we have at position 2 we have 2 blocks, at position 4 we have 1 block, position 5 we have 3 blocks, and at position 8 we have 6 blocks. We divide that through by the total number of blocks, which is 12, and we get this answer, which is close to 6, where we initially thought intuitively that it would sit, right? And this gives us the x-coordinate of the center of mass. Okay, so what if we want to apply this theory to an arbitrary shape, like this blob that I've drawn down here? Well, the first thing that we need to do is assume that it's got evenly distributed mass, so that we can say that the mass is proportional to the area, and therefore it suffices to find the centroid of the area to find the center of mass of the shape. Well, the first thing that we do is we split the shape into strips of width dx. So now at this point all of you are getting flashbacks to calculus, because all of this stuff here is coming rushing back to you. But basically what we do is, by splitting the shape up into strips of width dx, we can find the area of each individual strip, which I'm calling dA, by multiplying the width by the height, right? So the height I've just taken as y2 minus y1, and I've called that y. The width is dx, so dA is just the width times the height. And what I can do is basically redefine this formula that I had previously, where I take the position of each of the strips, multiply by the area of each of the strips, which these are all different now, right? And divide it through by the total area to find the weighted average. But what you will remember from calculus when finding areas via integrals is that as we increase the number of strips, or basically as these widths dx get smaller and smaller, the accuracy of our calculation of the area increases. So what we do is we consider the limit as the width of the strips dx tends to 0. And what that allows us to do is to write this formula here as an integral equation. So now we say that the center of mass, x bar, the x-coordinate of the center of mass, x bar, is the integral over the area of x dA divided by the total area. Or, if we decide to split our shape into horizontal strips, we can find the y-coordinate of the center of mass, y bar, as the integral over a of y dA divided through by the total area, which is given by the integral over a of dA. And together, these two things, y bar, x bar, y bar, give us the coordinates of the centroid of that shape, which is going to be here somewhere, right? So let's go ahead and look at a couple of examples then. So the first example that I have here is basically a triangle shape truncated at x equals 3. The equation of the line defining the triangle is y equals a half x. And the question is to find the x-coordinate of the centroid of the triangle. So the first thing that we need to do is split the triangle into strips of width dx, right? And to find the area of these strips, we need to know the height of the strip at each of these points. And the height of the strip is just given by the equation of the line defining the triangle, right? So in this case, the height of the triangle at any point x is just y equals a half x. So the area dA is just the width times the height. So the height is a half x and the width is dx, right? So now we can go ahead and plug that into our formula for the x-coordinate of the centroid. So we have the integral over a of x dA over the integral over a dA. We've worked out what dA is, and the only other thing that we need to do to write this formula in terms of the triangle is to define the limits of the integral. So here we're just dealing with the integral of this triangle between 0 at the origin and x equals 3. So that's what we're going to plug in to here. So we have the integral over the area that we're considering, in this case between x equals 0 and x equals 3, of x multiplied by the individual areas, which we worked out over here. So we plug all of that in. The next step, what I've done is to just simplify these expressions are in the numerator and the denominator a little bit. So I've multiplied this x through, I've taken the halves out because they're constants and then cancelled them, and then I'm just left with an integral equation that hopefully you're all very comfortable in doing. So I integrate the top, integrate the bottom, and then I work out by plugging in x equals 0 and x equals 3 into these expressions, I find that the x-coordinate of the centroid of the triangle is 2. So that tells us that basically the balancing point of the triangle is 2/3 the way along the triangle. Now that should be a fairly standard result that you're all pretty familiar with, and is quite logical when considering what's going on here with the equation of this triangle. So that's the first example. The second example is we're going to have a look at a slightly more complex shape, which is defined as the area between two lines, this straight line y equals x and the curve y equals x squared. And we're considering the centroid of the area bounded between those two curves. And in this case, excuse me, and in this case, the question is to find the coordinates of the centroid bounded between the two curves. So the first thing I do, as before, is I need to split up between the curves into strips of width dx. So we're considering the x coordinate of the centroid initially. So I split up the shape into strips of width dx, and therefore I can work out the height of each strip. So I always have the straight line on top and the curved line on the bottom. So the height of the strip at any given point is the position on the straight line subtract the position on the curved line, right? And therefore the area of each of the individual strips is just given by the width, which is dx, and the height. So that's fine. We can go ahead now and plug all of this information. And by the way, the two curves intersect at the point x equals 1, which is also y equals 1, right, from this. And that's going to give us the limits of our integrals. Okay. So we go ahead and plug that information into the formula as before. We consider the integrals between 0 and 1, right? Between the origin and where the two curves intersect. And I have x multiplied by dA, which I worked out here. Plug that in, plug in dA on the bottom, work out my integrals in the numerator and the denominator, and plug in my values to get x equals 1/2. So that tells us the x coordinate of the centroid, but now we need to find the y coordinate of the centroid. So what we need to do now is go back to the original diagram and consider what happens when we split the shape into horizontal strips rather than vertical strips, right? So that's what I've tried to annotate here, is that I'm now considering horizontal strips of depth dy, and then I can work out the width of the strips by basically rearranging these equations. So the curve is always on the right hand side, so if that is given by y equals x squared, that's the same as saying x equals the square root of y. And then I have the curve always on the left hand side, so that the width of the strip is always root y subtract y, which is what I have down here. So therefore the area of any of these horizontal strips is just given by the depth dy multiplied by the width, which we've just worked out. And the curves intersect at y equals 1, because we said they intersected at x equals 1, and we just have y equals x, right? So with this new information, we can go ahead and just plug this into the equation for the y coordinate of the centroid, which is exactly the same as the equation for the x coordinate of the centroid, but we're just replacing x's with y's, and remembering that everything is now in terms of these horizontal strips rather than the vertical strips. So I've plugged all of this in here, basically tidied it up a little bit, written these square roots as fractions so that they're easier to deal with the integration, and calculated the y coordinate of the centroid as 2/5. And therefore my final answer for the coordinates of the centroid is just given by the coordinates x bar, y bar, which is 1/2, 2/5. Okay, so that's it for this particular tutorial. Stay tuned for more videos and keep checking Canvas for more updates. So have a good day, and I'll speak to you soon.